Welcome back, everyone. Let's continue our discussion of polynomial regression by doing a train test split on our new polynomial feature dataset, and then also fitting training the model and evaluating it so we can compare its performance metrics to our original linear regression model. Let's head back to that notebook. Okay, here we are in the notebook. Where we left off last time is we had this polynomial converter object that can then fit transform any x dataset from 3 features to 9. 3 of those are the original features, 3 of them are the squared features, that is order degree 2, and then 3 of them are the interaction terms. So we're going from 3 features to 9. And now what we want to do is perform the train test split. As a quick note, later on when we read in a new data point with 3 new feature points, for example, we later on want to test on some sampling of TV, radio, and newspaper, because those are only 3 features, our regression model is actually going to be trained on 9 features of these polynomial features. So we will need to eventually save the polynomial converter in order to transform future data points. So just a quick note, later on we'll be saving not just the model, but also this converter object, since it's going to be necessary for new incoming data points where we only have the 3 original features. Something to keep in mind. For right now though, we're going to perform the train test split. So we say from scikit-learn.modelSelection import train test split. You should be able to autocomplete that with tab. And then what I like to do is, after calling train test split, do shift tab in Jupyter or call help on it to see the documentation string. Scroll down. At the very bottom you should see the example and just copy and paste it. That way you always make sure that you're doing the tuple unpacking in the correct order. So I'm going to copy this and then paste it back into this cell. And then there's a couple things to note here. The first one is that I'm not going to perform train test split on just x. Recall, x only has those 3 features. Instead, what I need to do is call it on the entire polynomial feature set. So we defined that in the last lecture as polyfeatures. Again, as a reminder, if we call polyfeatures and check its shape, it's the original 200 rows, but with those 6 additional feature values. Again, the 3 original, 3 interaction, and 3 squared terms. So we're going to pass in, instead of x, polyfeatures. Don't need to change anything in y since we're still predicting the same original sales value, but now we're predicting it off those 9 features. Test size and random state. In order to fairly compare my previous linear regression algorithm, I should choose the same test size and same random state as I did in the last project. So for that, we'll say 0.3 is our test size, and my random state, to make sure it matches with the previous lecture series on linear regression, we'll say it's 101. That way, at the end of the day, when I get my root mean squared error off the polynomial features, I will be able to directly compare it to my root mean squared error from the straight linear regression. Okay, so we'll go ahead and run that. I have now xtrain, xtest, ytrain, and ytest. After this, we're going to call a linear regression. So just as before, we'll say from sklearn.linearModel import linear regression, create an instance of your model. So we'll say model is equal to linear regression. Go ahead and just keep the default values there. And now it's time to fit the model. Model fit. And now I can use the same xtrain, xtest, ytrain, and ytest terms as before. The main difference was I passed in polyfeatures, not the original x. So let's go ahead and fit the model to xtrain and ytrain. Recall, this is now training a regression model on 9 features instead of just the original 3. So run that. You have your model. It's now fit. It's time to evaluate its performance on the test set. Basically, the exact same procedure as before. We go ahead and define a test predictions variable. Grab your model and say predict off the xtest set. Again, xtest is also 9 features. If you tried to pass in just 3 features, you would get an error here since it needs 9 because it has 9 beta coefficients. Run your test predictions. In fact, we can confirm these coefficients by checking them out here. Notice there's now 9 of them. So keep that in mind. And then let's go ahead and evaluate just the performance metrics. So from that, we can say from sklearn.metrics import mean absolute error, and we'll also do mean square error. So we have MAE, MSE. Let's calculate them. I'm just going to create 3 variables here. Mean absolute error. So this is on average, how far off are you? compare your y-test values to your test predictions, create a mean squared error, which is going to be mean squared error, again, y-test and test predictions. And since mean squared error is actually in terms of squared sales units, what I should do is call root mean squared error, which is kind of akin to the standard deviation. Instead of just variance, we'll call np.square root and call mean squared error. So the main ones I'm going to be looking at are MAE and RMSE, since I can interpret those in units of dollars. So my mean absolute error is 0.489, and then my root mean squared error is 0.66. So again, root mean squared error punishing my model when it's off, even on just a few data points, by a lot. So is this actually performing better than the linear regression from before? If you go back to the previous lecture and check out the values for linear regression that we did last time, we got a mean absolute error of 1.2 and a root mean squared error of 1.516. It's important to note that the only way to fairly compare your previous values is if you perform the exact same train test split in this model as you did on the other one. And we made sure that by choosing the same test size ratio here and the same random state, which basically grabs the same index rows as we did previously. So that's the way we're able to make sure of that. And so obviously our polynomial regression model is performing much better than just a linear regression. So clearly there is a case to be made here that we should be considering the polynomial features. And what you can do is if you wanted to explore this model further, you could take the model and explore its coefficients, and the coefficients are now just in terms of the polynomial feature values. So you'll have to go back, and especially for large polynomials, it becomes a little hard to decide which coefficient lines up with which variable. But the easiest way to do this is to check out polyfeatures 0 and compare it to, in our case, it's going to be XILOC 0. So recall we have 230, 37.8, and 69.2. Those are the first three features here. So I can see the actual beta coefficients now for the original features. Notice they're pretty small. And the other thing to notice is for some of these features, they're almost 0. So for example, the very last one here is negative 3.04 times 10 to the power of negative 5. That means it's basically not even considering this feature of that results in 4.788. If you want a reminder of which one that is, that's going to be one of the squared features. Specifically, it's the newspaper squared feature. So again, just to make it clear, we have here this beta coefficient, extremely small value. It's again negative 3 times 10 to the power of negative 5, meaning it has a bunch of zeros before or after the decimal point here. So this value is almost 0, meaning it's not considering this particular feature, and this feature is newspaper squared. We can confirm that by checking out 69.2 to the power of 2, and it's the same value here. So essentially, in our first linear regression, we weren't really considering newspaper, which makes sense that now, when we're squaring things, we're definitely not going to consider the squared newspaper value on its own. But clearly, there is some positive correlations or positive beta coefficients that are quite strong. Notice we have very strong beta features or beta coefficients for the interaction terms. So there's a lot of synergy going on with some of these advertising methods. Okay, so lots of interesting things here. Again, main things to consider is when you're performing your model training, you want to make sure that you're passing in the polynomial features on your train test split. Don't accidentally pass in the original X values there. Coming up next, we're going to describe on how to choose the best model parameters. So the next step here would be to adjust model parameters. And while we can't adjust anything on linear regression, we can definitely adjust the level of the degree we choose beyond just degrees equal to 2. We could do degrees equal to 3, 4, 5, etc. on polynomial features. How do we actually decide which degree is the best? To fully understand that, we need to have a quick aside to talk about overfitting and underfitting. I'll see you at the next lecture.